Do you know what they call the last few graves in a cemetery? The residual plots. And we are getting to our residuals today, the last few bits of statistics. And the reason we'll be doing that is because we're doing linear regression, and part of checking our linear regressions is checking our residual plots. But first, linear regression. You did this in the fall, and we had the model. This is straight off your math chart. Y hat equals beta naught plus beta 1 times x, where beta naught is the intercept and beta 1 is the slope. And we would do a fit to that using least squares. Remember, the residuals were the smallest squares. So the correlation R, that's the number we get back out, would indicate the strength and direction of the linear relationship. So the sign of R provides the direction, and the absolute value of R provides the strength. Just a quick review. These are just kind of guidelines. Strong is anything between 0.8 and 1, or negative 0.8 and negative 1. So 1 is the absolute highest that R can be. Negative 1 is the absolute strongest negative direction you can have. If you are between 0.8 and 0.5 in either the positive or negative direction, that's considered a moderate relationship, and anything in between is considered weak. Now, R squared provides a percentage of variability that can be attributed to the linear model. We still have the same conditions and assumptions. There's a linearity assumption or straight enough condition, and that's satisfied if the scatter plot looks straight enough. But you really should verify this with a plot of residuals, because that's sometimes very hard to eyeball. The residuals, if you see any curvature or bend, then maybe a linear regression is not the most appropriate. Independence is the same as usual. One point shouldn't really affect another point when you're gathering your sample. All right. Does the plot thicken? So we need to look at the residual plots and see if the spread is fairly consistent. If it's like really thick to one end, maybe there's a nonlinear relationship there. Not sure. Nearly normal condition, that's the unimodal and symmetric that we've been working with. Take a note of any outliers you see. You may not be able to justify taking them out for your fit, but you at least want to acknowledge them, all right? And also check the modality with the histogram and the symmetry with a box plot. Box plots are also great for pulling out outliers. All right, so first of all, we have Olympic long jump records. We're going to look at this as an example. And this is data off the internet. It is the long jump records from 1900 to 1996. And there's really a nice article, and I'll put a link to it on the website, about this amazing long jump that I have highlighted and read in 1968. Okay, so we make a scatter plot of the data. That looks pretty linear. It doesn't look like anything crazy. So it looks like it satisfies the straight enough condition. There's no obvious bend in the plot. Independence. Well, I'm not really going to get that information from the scatter plot, but there's no reason to believe that the long jump record in 1952 is dependent on the one in 1948. So we're going to assume it's reasonable. Does the plot thicken? Well, we have to wait until we do the regression, and then we'll do the residual plot. The nearly normal condition, again, we're going to wait and do the regression first. So let's go ahead and do this linear regression. Basically, make sure you enter your data onto list. Here I just did list 1 and list 2, so you can see all the years and all the data. Then, make sure your diagnostics are on when you're doing your linear regression. There's my graph and my scatter plot that I showed you last time. So if you don't have your diagnostics on when you do line reg, you are not going to get R squared and R. Now, here I'm listing my X and my Y values separately. Since I'm actually using list 1 and list 2, that's not really required. But it's kind of nice, especially if I decide to use other lists for the data, then I really do have to do line reg. And then list 3, comma, list 4 if I'm not using list 1, list 2. So you see, you have to make sure you're using the right list for your linear regression. Okay, so there's the results from our linear regression. And the way we interpret it, for every increase in years, so for every 1 year that it goes up, we expect an increase of 0.61 inches in the long jump. I should say 1 year here, that would be better. R is 0.90. So there's a strong positive linear correlation between year and long jump record. And R squared is 0.81, so we can say 81% of the variation in long jump records can be explained by the linear regression model. Now let's go ahead and check our residuals. The way you want to do that is make sure that you go hit stat plot. And here I'll show you how to do the both the box plot and the scatter plot. So first of all, we got the scatter plot here. Go ahead and hit graph. And you can see the residuals there. There doesn't really appear to be any thickening, all right? So we're probably okay there. So there's my residuals plot, straight enough, no obvious patterns. Now I'm going to do a histogram, not a histogram, a box plot. And there we go. That'll help me check for modality. Since I'm doing a box plot, I want to make sure I'm doing the residuals. Hit graph, and it needs to zoom. And there you go. So there's my box plot. And one other thing, I didn't do it on the video, I also created a histogram of the residuals. So I do meet the nearly normal condition. The box plot is fairly symmetric. I'm a little concerned about this outlier, but if you look at it on the histogram, it doesn't look like it's so far out that it's really going to be a big deal. You would always mention it though. And this really does look unimodal. To me, it looks a little skewed, but using the box plot, that's roughly symmetric. So don't say it is symmetric. You could say roughly symmetric.